post it. Okay, so here we go. We're going to go into chemistry, and you know a bit about chemistry from last lecture. We talked about, again, I mentioned before, the proton, the neutron, the electron. So you're going to hear things like mass. Mass is weight, really, but weight without gravity. Okay, we're going to talk about bonding between those elements to form molecules. So let's talk about a couple of things we already talked about and how it's going to relate to chemistry. Remember, what does sodium look like? Sodium, that's Na. That's the element, but we're going to talk more about the ion. And that's a positive ion, also known as a cation. So let me ask you this. Does the sodium, does it lose an electron or gain an electron to become positively charged?
It loses an electron.
It does, because electron is negative. Bye-bye electron. And then we can talk about chloride too in that vein. So chloride's more likely, chlorine, I should say, is more likely to do what with the electron? Lose or gain?
Gain.
Gain, that's true. It's true. So these two like to really bond together, right? This is the salt. NaCl is salt. The salt you use on your, well, where did we eat last week? Was it Popeyes? Let's go to Chipotle today. Chipotle. You can put salt on Chipotle, but it probably has a lot of salt to begin with. So that's sodium chloride. You might put some out on the ice so you don't slip. And there's other types of bonds. This is an example I'll tell you right now. This is an example of a pretty strong bond called ionic bond. And then we need to talk about, remember this? This is an ion too. Hydrogen, remember, that's easy because hydrogen has an atomic number of 1, which means it only has 1 proton. Hence, it only has 1 electron. So it's really easy for a hydrogen atom to lose an electron and become positively charged. So let me ask you this. Does this H plus hydrogen ion, is that acid or base? Base is also known as alkaline.
Acidic.
That's acid, right? Right. Remember, pH is the percent of hydrogen. See, we're biologists becoming chemists real quick. Not me, really. Then you might see something like this. This is called a hydroxide ion. And this is more alkaline or base. Means the same thing. It's all about the base. So if I put those two together, what do we have? How many hydrogens do I have? Quickly, how many?
2.
2. How many oxygens?
1.
And what does that make? What's this molecule?
Water.
That's true. You got that right. You got that right. That's not an ion anymore. This is a nice molecule. This is our favorite molecule in our body. It's our most abundant molecule in our body. It's water. Can I say water instead of water? Okay, so this is H2O. This is water. So everything, this is the universal solvent. This holds a ton of heat before it even goes up 1 degree. Its high heat capacity means when we get hot, we release water to release the heat from our blood. Our body temperature goes down. Crazy, right? So all our reactions, we talked about anabolic, catabolic reactions, they all happen in the presence of water. Guaranteed. Hydrolysis, dehydration. Hydrolysis, dehydration. Hydrolysis means you add water to break things up. Dehydration, you lose water, right? Dehydration. Cool. Then it gets a little complicated. Then you see something like this. And I like this molecule because this is a good buffer. This is a buffer for acid and base. So this will take the base and the acid, the acid and the base, and it'll take in carbon dioxide, right? H2, that's our carbonic acid, but let's just talk about the ion. And this is the bicarbonate ion, HCO3 minus, I didn't want to put the 2, that's carbonic acid. So if you put all these 3 together, you're going to get carbonic acid. So acid is going to ride on this HCO3. So a buffer is the bicarbonate ion is going to buffer acid, basically. It's a kind of a weak base that turns into a weak acid. So you ever heard of the bicarbonate ion, right? You ever have a bellyache, like if you ate too much Chipotle, and then you have acid stomach because you have so much of this going on? You might go buy a bicarbonate to neutralize that acid. And your blood is doing this all the time. Because what did I say the pH of blood should be?
7.4.
Thank you. 7.4. I know about the range. I know all about it. I went to college. I know that there's a 7.35 to 7.45 range, but it's a compensatory range. This is where we want the pH of blood. So this buffer, the bicarbonate ion, tends to keep the blood a little bit alkaline. Beautiful. So then the organic macromolecules, let's go through those. What's the one we want to use for energy? Begins with a C, ends in an 8.
Carbohydrate.
Right on. So this is the one we want to use for energy. So we're going to break that down to glucose, you'll see. And what's the other one that we only use for structure? Begins with a
Protein.
Protein. And what's the one that steroids are membranes are made of
Lipids.
lipids, right? With fats. Fats are triglycerides, basically. Excellent. And what's the DNA, RNA, and ATP? Where does that fall under?
Nucleic acid.
Nucleic acids. Beautiful. And they're all organic, means they have carbon. They have some hydrogen, a lot of hydrogen actually, oxygen, and sometimes nitrogen. So these are organic molecules, and they really make up most of our body, besides water, right? And if I ask you, is water organic? It's no, it's not. It's not. So we talked about atoms already. Remember, John? And in great amounts, each one of these, I'll refer to it as an element. Ions are really our electrolytes. Let's get that word up there, if I could spell it right. Electrolytes. You've heard of those, right? Potassium, calcium, sodium, chloride, magnesium, all charged atoms. And then we're going to have some bonds. Bonds, and that's going to be about what's happening with the electron. The valence electron, you should know the outer shell electron. So all the processes that happen in biology are based on chemistry. So we could have a really big war between biologists and chemistry of what's more important. It'd be a big East Coast, West Coast, blue state, red state thing. I don't want to get into that. So let's all get together and say it's all important. But really the smallest part of life is a cell, living thing. We talked about that last time. So it doesn't say life, right? Smallest part of an element. The element is the chan or other atoms or other elements. Okay, so you have the positively charged protons, the uncharged or neutral charged neutron, and these two have basically the same weight. They have mass. Mass, they're matter, so matter means it has mass and it takes up space. Okay, but then you have these orbiting outer particles called electron with negative charge. So if I ask you what the atomic mass is, you have to add, all you have to do is add up the number of protons and neutrons, and it's usually the same. You're going to hear what an isotope is, but usually it's the number of protons equals the number of neutrons for the most part, for what we're talking about. Okay? And the atomic number, if I ask you for the atomic number, you're going to give me the number of protons. So the atomic number of hydrogen has 1 proton, so it's hydrogen 1. And here's like a theoretical look at all this. You could see hydrogen 1, just 1. Here's the blue proton. Here's the party guy out, the electron out here. Okay, carbon, this is carbon 6, atomic number of 6, which means it has 6 protons. If you put the two together, you get the atomic mass of neutrons and protons, and you get the atomic mass, which is 12. And 6 electrons. So maybe you have to learn this. It's kind of simple. But you see, you have what's called a nucleus. I don't want this to get confusing with the nucleus of a cell, but the nucleus of an atom is where the protons and neutrons live, the particles that have mass and take up space. And then there's an electron shell just outside the nucleus, and that can only hold 2 electrons. I don't make this stuff up. This would give me a headache. Einstein's probably going crazy trying to figure this stuff out. So that leaves 4 more electrons. So there's 4 electrons in the next shell. And this happens to be the outer shell for carbon. So each subsequent shell outside the first shell can hold up to 8 electrons, and that's called the octet rule. And the outer shell is always called, even here, is always called the valence shell. Now, once you get friendly with the electron, you guys become friends, you can call that outer shell electron just a valence electron, because that's the one that's going to party, especially this one, right? It's going to find an oxygen, right? Eventually become water, because that's a really big inorganic molecule in our body. So this is just explaining what I just said, the orbitals, and we call it the octet rule, if you want to impress your friends. And that means that there's only two electrons in the first shell from the nucleus, and then each subsequent shell holds up to 8. Okay, so you might have to do a little bit of figuring on that when you find out the atomic numbers, of course. Okay, so this is important. Sometimes I'll mention something is stable. So atoms are most stable when the outer shell is filled with 8 electrons, of course. But then if you lose one, or there's one less, or 2 less, or there's only one, that really gets volatile and wants to bond, which are good. So those are the valence electrons. And this is really what gives energy to the universe, this positive, negative polarity I mentioned last time, right? Polarity, so you should know what polarity means. I always like these tables. I always like you to take a look, and this book does a really nice job. Catherine, you'll see when you read the book, it's pretty good. So here's Sean. They don't like my acronym for it, so they do it different in number order, which is probably makes more sense. So let's just look at this real quick. How many protons are there in oxygen? Not oxygen gas, of course, is oxygen the element.
8.
You got it. You saw the atomic number, smarty pants. Very good. Very good. So then you could figure the octet rule, and you could find out the atomic mass by adding the protons and the neutrons. But look, it's the same thing. It's like adding the protons. So it's just doubling the number of protons pretty much in a stable atom. Sulfur we're not going to talk that much about, but it's fun. It's fun to talk about. And this kind of gives you a cheating way to learn of course, it's always 2. It's always 2, right? And then this way here, you just have to fill up the shells according to how many electrons they have. So technically, how many electrons does stable oxygen have? And the answer is 8. The answer is 8. So 2 are in the first shell outside the nucleus, and 6 in the valence shell. And that's the end of it. There's no shell 3. There's no shell 3. Okay. So that leaves 2 spaces for electrons. Make sense? Is it making sense to anybody? So it could pick up and share electrons with 2 other elements, which you'll see. And we're going to keep that really simple. You're not going to have to do a lot of figuring on that. Isotopes, here's what you should remember at isotopes. Isotopes has the same number of protons, but the number of neutrons differ. Got it? So if carbon, which is 6, right? 6, carbon is 6, atomic number of 6 protons, but sometimes it has 8 neutrons. And then what would be the atomic mass? If it were normally in the stable carbon 6, which is carbon 12, the atomic mass would be 12. So how many neutrons would carbon 12 have? Anybody with me on that?
6.
6, right? Because they're just adding the protons and neutrons. But if you had 8 neutrons, then we'd have to call it, we can't call it carbon 12 anymore. What would we call it?
Carbon 14.
You got it. And that's an isotope. Usually isotopes are not stable. They don't live as long as the stable one. This has been around forever. We can carbon date, right? We could use isotopes and find out how old my uncle Jeremiah was 140,000 years ago when he was swinging on trees, right? If we find him, if I could dig him up in the basement. And other things too, anything that has matter. Carbon's important because it's part of organic molecules. It's amazing. Okay. So the atomic mass is different because of the number of neutrons is different. And isotopes are what's called radioactive, right? Radioactive. So we could, so how does this, let's see, how does that correlate? I love doing clinical correlations. So we use it for medical testing and physiological research. This is physiological, this is human physiology, but this is important. So what does an isotope do? Like, how do we use it? Anybody know off the top of your head? Or the bottom of your head, whatever? What does an isotope do?
Sometimes used to like target cells and stuff.
Yeah. So I think there's some radiology people in here. So that's kind of important to know about that. Okay, I can't get my virtual background. This is kind of bummer. So there it is. So what do you call it when, let's say I want to look at, what are we looking at here? The heart. You see behind me, you see the X-ray, there's a heart back there. So we could use a radioisotope like tritium or something like that of another element, and we inject it into the blood. And the blood cells will be tagged with this radioactive isotope. And when you take an X-ray, if you see behind me, it's mostly dark shadows, like the bones and the thickness of muscle will show white and the space will show black. But if you have the isotope attached to your blood, you might be able to see the coronary arteries. And we call that an angiogram. Like angio means blood, gram means like an X-ray, an imaging. So you could do that for the brain, do an angiogram of the brain. You could do it of any vessels in the body. You could do it of the kidney, the liver, you might want to do it. Okay, so that's kind of important for that. So those isotopes are important, and that's how we're going to relate it to physiology. You might use it for research. Sometimes you use it for treatment too. Okay. So that's when we say element, like carbon, we're trying to include all the isotopes within that group. So that's pretty good. Remember what isotope is, and that varies in its neutrons. Chemical bonding, again, this is pretty much going to be all about the electron. Remember the electron, he or she just loves to go out and party. Okay, so atoms are interacting via their electrons or lack of electrons. And of course, the valence electrons, the one that are in the outer shell, are really important. Okay, hydrogen is always easy because it has one electron. So it's really lonely in that valence shell. There could be two, right? But there's only one. So carbon is a little different because it has four valence electrons, and it can get a couple of extra, right? It can get a couple of extra. It could bond with other things very easily. So the organic molecules, of course, there's a lot of carbon-hydrogen bonding, but you'll see. I don't want to rush to get there. I know that's the most important thing is the organic molecules, but we should go through all this inorganic stuff since we're together. So covalent bonding. Covalent bonds. Have we talked about another bond yet? No. Chemical bonds. Yeah, I'm just going to say covalent bonds is the first type of bond we're going to talk about. Okay, because there's another one I mentioned before called ionic. And I don't want to mention that just yet. Okay, covalent. Here's what you should know. Covalent bonds, atoms, and here's the big word, share electrons. So whenever you hear covalent, it's about sharing. And there's two different types of sharing, which is important. So in this case, electrons are shared equally. If they're shared equally, which means they're both using the same electrons to share. So like two hydrogens. So again, I can't say that's water because water is definitely not sharing equally. It's sharing unequally. So if it shares equally, it's called nonpolar. Nonpolar. Okay. So that's a nonpolar covalent bond. Okay, nonpolar. If they're not shared, or I like to say they're shared unequally, then it's a polar covalent bond. So let me draw this out for you. This is where you need to know. So remember that molecule, I'll draw it like a mouse. That's really important. Where you have oxygen. This is the oxygen, and this is the hydrogen. Are you with me? So oxygen can share electrons with 2 hydrogen. So, but oxygen tends to be, it's bigger, first of all. It tends to be more electronegative, where hydrogen lost an electron, so it's going to be more positive. So the bonds between hydrogen and oxygen, like both of these bonds, are always polar covalent. They're sharing unequally. Okay? And you don't have to know exactly. I'm not going to make you draw this out. I'll make you draw this molecule, but do you understand that these bonds between oxygen and hydrogen, this is only one molecule of water. These are polar covalent bonds. So I think what I want to give you here, what I want your takeaway to be, that water is very polar because of this bonding. Did we talk about polar last time? We mentioned it a lot, right? Like, let me ask you this. I know I got to keep you up to speed here. I mentioned the 3 macromolecules. Did we eat a Popeyes last time, Gabriella? Yeah. So the protein was the meat. So that proteins are very polar. They're hydrophilic. And basically, they're non-lipid soluble. Carbohydrates, I think that was the biscuit, right? The biscuit in Popeyes. That was polar, non-lipid soluble. Okay, hydrophilic, of course. And this is really why. It's because of this non-polar bonding. And there's more to water than just that. So lipids are different. Lipids are going to have more non-polar covalent bonding. Could you imagine that? You see how this is all working out together? So it's kind of tough to figure out what is he talking about, polar and non-polar, but you're going to see as the reactions come into play. Okay, covalent bonds are sharing. This is 2 hydrogens, kind of simple. Sharing these electrons together. It's a very nice setup. So that's covalent bonding. They're sharing. They're sharing, right? This is CH4, which is methane, right? It's a gas. And they're sharing bonds. Okay, these are nonpolar covalent bonds. They're did I say sharing bonds? They're sharing electrons. Thank you, sir. Thank you, madam. Have a nice day. We're sharing. Okay, they're sharing 4 pairs of electrons covalently. And this is the most, and I would say, I have to say that, and I remember this, that these covalent bonds, especially the nonpolar covalent bonds, are the strongest bonds you could have. Strongest bond. It's stronger than ionic and definitely stronger than hydrogen bonds, which is probably the last one that your book will talk about. Here's ammonia, 1 nitrogen and 3 hydrogens, so sharing 3 pairs of electrons. Covalently, covalent bonding. And it all has to do with how many electrons are in that valence shell. And it all works out to a nice, stable compound molecule. Compound molecule means there's more than 1 element in it, more than 1 atom type. Wow, so we're getting right into water like this. Katrin, you'll like this. This book is very good. So water, H2O. Remember, what type of bonds are between hydrogen and oxygen? They are polar covalent bonds. Remember my nice little drawing with this? Usually, sometimes you draw a double bond with 2 lines between, but these aren't double bonds. They're not sharing 2 pairs each, right? It's just 1 pair of electrons being shared with those 2 polar covalent bonds. There's the hydrogen. And the hydrogen tends to be more positive because it has no electrons left. The oxygen tends to be more negative. I have to keep saying that because that's really important. So this water is extremely polar, and that's the reason. This oxygen is so big. It has more electrons than hydrogen because hydrogen has no electrons left. It's sharing it. So hydrogens tend to be more electron positive in the water molecule, where the oxygen is more electronegative. You guys understand that? That's kind of important. So in this big molecule of water, you have this polarity. You have negative at the oxygen, positive at the hydrogen. And that's what gives it its polarity. It's a miraculous molecule. And it's a good solvent. I think I made that straight. You know, all the reactions can react within it, and all the solutes dissolve in it. What are solutes? Let's talk chemistry. Solutes: sodium, potassium, glucose, hormones like estrogen, amino acids. I can go on and on. Fatty acids, cholesterol, all those things are in the water. Some of them dissolve better than others. Like I said, fatty acids. That's not going to dissolve in water so easy. Why? Because it is, what's a good word to use? Or let's say cholesterol. Cholesterol is a lipid. Everybody got that? Cholesterol is a lipid that is the basis for all steroids: estrogen, testosterone, cortisol, progesterone, aldosterone. They're all steroids. So cholesterol is the base for all of those. So cholesterol is a lipid. So what would you say about cholesterol as compared to glucose? Glucose is polar. Glucose is hydrophilic. Glucose is non-lipid soluble. So cholesterol is all the opposite. Cholesterol is non-polar. Cholesterol is hydrophobic. Cholesterol is lipid soluble. And it all has to do with this chemistry. And we mentioned this last time. Cool. So later on, we could form hydrogen bonds. And I should talk about that now, but I'll go back into what hydrogen bonds are. But I'll give you a little breakdown. Let's say, here's oxygen. Are we clear? I don't have to draw this in anymore. Here's another water. Here's another water. But of course, there's thousands, millions of these, right? So oxygen tends to be electronegative, and hydrogen tends to be electropositive because of the electron situation. So now we're going to have like a weak bond that's going to be between hydrogen and oxygen. And I should draw that in dotted line so it makes sense to you. You're going to have a weak bond between all the oxygens and hydrogens in this water sample. Right? You're going to have one here like this. And it's going to continue like this. All right? And this hydrogen is going to bond to this like this. And all the electronegativity will bond to the electropositivity, if you will. So all these dotted lines are hydrogen bonds. So basically holding all these molecules together is this weakest bond called hydrogen bond. And that's based on polarity too. And this is really what gives water as a fluid, as a solvent, its miraculous qualities. So hydrogen bonding holds big structures together. I can't draw helixes, but what's that big helix like double-stranded thing that kind of holds
DNA.
DNA, right? It's double-stranded, right? Did I say double-stranded? RNA is only single-stranded. So what type of bonds hold these big structures together? It's hydrogen bonds. So the hydrogen bonds hold large structures together, like the two strands of DNA are held together by hydrogen bonds. What's that big? It's not big, it's pretty small. What's that protein in our blood that carries oxygen?
Hemoglobin.
Hemoglobin. Hemoglobin is made of two polypeptide chains, which are really two proteins. And they're held together by hydrogen bonds. So the hydrogen bonds give shape by connecting two large molecules, like two proteins together, or two, you're going to learn it's a polypeptide. My definition of a protein is 50 amino acids or more. So if it's less than 50 amino acids in that chain, I call it a polypeptide. And you'll find out what that is when we do the organic molecules. So water is polar molecules. And polar molecules can dissolve in polar molecules. That's why they're called hydrophilic, like glucose, amino acids, hydrophilic. Fatty acids and cholesterol are hydrophobic because they are lipids. Makes sense to me. So yeah, this is no joke. Nonpolar molecules do not dissolve in water, and they're called hydrophobic. So cholesterol is hydrophobic. Get it? Proteins, amino acids, and glucose, carbohydrates, they are hydrophilic. This is where we're going with this, to the organic molecules. Whew. Here's water. I like the way I drew it better. I don't care. I don't care what you say. So the oxygen is the big fat guy, and the hydrogen are the little yellow dudes, right? So oxygen tends to be the little omega, says it's electronegative, and hydrogen is more electropositive. So it has a polar covalent bond. So these two bond, the bond between, you can't see red, but the bonds between these two are polar covalent, right? But this bond between the hydrogen and the oxygen, let's say, that would be a hydrogen bond, but this is not really drawn to scale. It's breaking up, right? And what does it break up into? Hydroxide and hydrogen, both ionic. So which one's the base? A or B? Which one's the base?
A.
A, you're right. This is base. So more hydroxide, higher the pH. More hydrogen, lower the pH. And you have to know it's an inverse scale. That's kind of creepy. So I think I mentioned it last time. Anything below 7 in a laboratory is acidic. Anything above 7 in a laboratory is alkaline or basic.
Can you repeat why it's why the base is lower pH, or did I just mix it?
Yeah, it's a weird scale. It's a completely, it's negative numbers. Like, yeah, it's really hard. There's a picture coming up, but it's a negative
That's
number.
fine then.
Like 14 is a high pH. Everybody agree? It's a high pH, so it would be alkaline. That's the end of the scale. So it's really negative 14. So it's the negative number of the percent of hydrogen, where pH of 1 is 1, not negative 1. So it's an inverse scale, and that is confusing, but it's easy to memorize, right? Once you have that down, you'll never forget it. You always know that below 7 is acidic, and in the blood, below 7.4 is acidic. So low numbers, acidic, higher numbers, alkaline. Because of the inverse scale, it does raise that question, and that's why. And I think your book gives you a little equation to do it, which I won't do. I won't give you that equation to do. You just have to remember.
So, Professor, the more positive, electropositive the hydrogen is, so the more hydrogen you have, the H plus, the lower on the pH scale it is, versus the oxygen raises it because there's more electrons, like gains electrons. Am I understanding that correctly?
That's possible. That's possible, but you don't have to go that far. You don't have to go that far because there's so much hydrogen ion in your body that it disperses because everything's in water. So it's the free hydrogen that causes the acid. And can it be neutralized through an electron? Yes. Like if you add it to the bicarbonate ion, that will, create what's called carbonic acid. So it binds more with that bicarbonate ion. So this is carbonic acid. So this is really how the hydrogens are carried in the body. Not so much in water. That's a good question. That's a good question. And it would go the opposite direction if it was hydroxide. Hydroxide plus water, right? Plus hydrogen, sorry, gives you water. And then you'd have to add carbon dioxide because carbon dioxide, and you should know this, excess carbon, let's learn this right now when we talk about acids and base. Excess carbon dioxide in the blood, which we hate, will give you increased free hydrogen ions. Are you with me on this? So carbonic acid is the carrier for the hydrogen, and really bicarbonate ion bonds with it to form the carbonic acid. And I'll show you that later. I'll show you that. I don't want to get ahead too far, but I like this concept when it comes to physiology. Think about this. In medicine, right? What conditions can cause excess carbon dioxide in your blood? Think about it. Anybody know? In a respiratory condition?
Poor respiration.
Yeah, it's
Constriction.
poor ventilation, right? Poor ventilation means like you can't really get that that carbon dioxide out of your lungs, which means you can't get it out of your blood. It'll back up in your blood. This is heart muscle behind me now. Don't get too excited. I'm trying to keep you off the chemistry thing. So, so a condition called emphysema. Anybody hear of that? Or chronic obstructive pulmonary disease, COPD. You're gonna hear that a lot. COPD. There's all commercials like with the people look great, but if you really meet somebody who has COPD, that's long term. It's not good. So COPD, usually they cannot exhale all the carbon dioxide out because they have a problem with their exhalation. And the carbon dioxide builds up in their blood. So if carbon dioxide builds up in their blood, what's going to happen to the pH of their blood? Is it going to go up or down?
Down.
It goes down and makes the blood more acidic, which our bodies do not like. That's a homeostatic feedback mechanism that has to work. So the kidneys and the lungs work together to maintain that pH of 7.4. So the compensatory range is all about, the lungs working with the kidney to solve the problem. Like, let me ask you this. I know, I'm sorry to keep getting in your face, but like say I have a respiratory problem, like Chris is saying, COPD, and my blood pH goes to 7.2. I have acidosis in my blood, period. Even if I was 7.35, I'd still have acidosis. And let's say that's even better. Let's say my blood pH goes down to 7.36, which is in the compensatory range. So if you look in the book, it'll say normal pH, homeostatic pH is 7.34 to 7.45, or 7.35 to 7.45. But the only reason you have that range, because if my lungs can't get rid of the carbon dioxide, it's going to lower my pH. But what other organ will wind up excreting the hydrogen ions or reabsorbing the bicarbonate ions to get that pH up? If my lungs are bad, I have emphysema, what other organ in the body will help and compensate for that pH by reabsorbing more bicarbonate and secreting and excreting more hydrogen ion in the pee-pee, if that helps you? So what organ does that?
Kidneys.
The kidneys. How's the wife in kidneys? Yes, the kidneys. So that compensatory range is kind of just allows the kidneys to compensate. It's not going to fix the problem. Just because my kidneys are spitting out hydrogen ions into the public sewer system doesn't mean I'm fixing my acidosis from my emphysema. It's definitely not fixing my emphysema.
So is that the reason why like you're able to live with COPD for a long period of time? Because of the compensation? Oh, I think you're muted.
Well, you have to, live with assisted oxygen. So, and you take medication to help oxygenate and help diffuse the carbon dioxide out of your lungs. But it's not a good condition. And yeah, the kidneys it'll keep you hanging on as long as your pH doesn't fall below 7.35. Sorry. That's a good question. Everybody understand that? So we're already into physiology. We didn't even get to the pH stuff yet. Love it. Love it. Make sure I don't mute myself again. Although you would love that. Okay. So ionic bonds, they save that for last. And this one is about, remember I said covalent was about sharing? Well, we're not sharing now. Now, ionic bonds, we're losing or gaining. The electrons. So this is like your salt bonds. These are pretty strong too. This is like your sodium chloride or your calcium chloride or calcium carbonate. So one atom gives, the other one takes, pretty much. So you have a donor and a receiver. No sharing. All right, one completely loses. It's a pretty good bond. It's a crystallizing bond. So this is important with cations like That's a cation. And I might have mentioned it last time, but a cation is a positively charged atom, like sodium. Potassium is a cation too, potassium. All right, so chloride is really the big one that everybody talks about. That's negative, and that's an anion. So if you can remember that, I always remember because there's a T in cation, and it looks like a plus sign. If that helps you, I'm terrible with mnemonics and acronyms, but if that helps you, cations are positive, anions are negative, and I will ask you that kind of thing on a quiz or exam, whatever. So it's very attractive because there's a polarity that, and you know, like unlike charges will attract, which gives everything energy. So it's a potential energy, really. Potential energy. When it interacts, that's when all the action happens. And we'll talk about the cell membrane. That's going to be really important. So I'll start talking about the cell membrane in this chapter. So it's not the strongest bond, like it says here. Covalent is the strongest. And hydrogen is the weakest bond. Makes sense too. Holding DNA together. So this is important because you really only have, like in sodium, you only have one. If you count it up, like sodium with its 11 protons, you count 2 in the inner shell, right? Octet rule, then 8, right? And then that 1 out there. Okay, so it's 11. I'm sorry, 11 protons, right? So it has 1 in its valence, so it's more likely going to give away. It's lonely, so that electron wants to get out. Now, chloride has 17 electrons. So it has 7 in its outer shell. So it's more likely to accept it. And this is the clearest thing. And this is the one I would give you. I'm not going to, again, this is not a chemistry class. But you have to understand this electron and how it works. And what's polar, what's nonpolar. What's an ionic bond? What's a covalent bond? What is a hydrogen bond? Really important. So here's the stable, ions. And if you put these in water, they'll break up nicely because it mixes well. Salts are easy to mix in water. They break up nicely, as you see, like sugar too. It'll settle out in a crystallized form though. So most ionic compounds dissociate in water. Most, they come apart with no reaction, no energy needed really. Okay, so remember what a cation is, remember what an anion is, and how they are attracted to each other, very strong attraction. Okay, so within water is where all these reactions are going to happen. So free ions, I think I made this clear, are critical in many physiological processes like sodium. Let's talk about sodium. Sodium. Probably the most abundant extracellular ion there is. And what does that mean? Extracellular. So let's get in your face again. So sodium ion is between cells, in the fluid between cells, which you're going to learn about. So you're going to learn about the cell membrane of every cell. And it's partly hydrophilic, it's partly hydrophobic, it has phosphate, it has lipid, but it's mostly lipid. So outside the cell is an ocean of fluid, like it's everything else. And inside the cell is just the intracellular fluid, or the cytosol, which we'll talk about. So sodium lives outside the cell. And what charge does sodium have? Is it a cation or an anion?
Cation.
Yeah, it is. That's a positive charge. So the outside of the cell is going to be what? More positive or negative, like the outside of the cell membrane? Because of all the sodium, it's going to be more what?
Positive.
Yeah, it is. It is. So I'm trying to put this together, this chemistry. Now, inside of the cell. So the cell, let me just draw the cell membrane, what it looks like really quick. It's got a biphospholipid layer. And sodium's on the outside where I drew it. But this goes on and on across the whole membrane. They look like balloons with 2 tails. So this is the membrane here. This is outside the cell, which we call extracellular fluid. And the inside of the cell is called the cytosol. So I need to really get this into your head right now. So you told me, and you were correct, in the ECF, which is an ocean of fluid outside the cell, between all cells, is positive, always, in a resting state, at least. The inside of the cell, listen to this, the inside of the cell, the cytosol, which is a little pond compared to the ECF, is negatively charged. So you see what's happening here? The outside is really positive. The inside is really negative. So that creates a polarity. And it has a potential, but it's not exciting. So in order to depolarize a membrane, sodium has to come in. And that's where we have excitement. So why is this important? Because you're going to learn two types of tissue, which we talked about the tissue, right? What are the four tissue types? Epithelial was one, right? Remember that one? Connective tissue is another, and we'll go through all the tissues. But what are the other two?
Nervous and muscle.
Yeah, nervous and muscle. And I'm sorry if I insulted the muscle tissue last time by saying it wasn't the brightest tissue, but muscle needs an impulse from the nervous system. So the nerve tissue, of course, is our brain cells and all the nerves that run to all the different parts of our body. You know, if we're eating our burrito here in Central Park and I have to either run away from the bear or fight the bear, my heart rate's got to go up. It's all nervous system stuff, right? Even though my heart has its own automaticity, like my friend behind me here. So what's my point? This is my point. The nerve cells and the muscle cells have excitable membranes, and the muscle's not going to do anything unless it's excited. And what excites it? Depolarization. And it's polarized, but when sodium comes in, that depolarizes the membrane of a muscle, and it goes crazy, and then it could contract. Same thing with nerve cells. So if I want to move my pen, it starts in my cerebral cortex. I have to think about it, which is voluntary, but I have to get depolarization all the way down to my fingers and my arm. So it's all about sodium coming into the cell and changing the polarity of a cell. So that's why this ionic thing is important. Yeah, we're not doing chemistry. I'm not going to give you chemistry equations. We have to know what this means in physiology. Crazy stuff. Okay, this is just showing the sodium within and you should know this is water by now. This is not Mickey Mouse. You know which one's the oxygen, you know which one's the hydrogen. So again, it dissociates very easy. Sodium chloride will dissociate. That's what this is showing. Okay, hydrogen bond is the weakest, and it has to be between two polar molecules. Like DNA, of course, has rows of nucleotides, and they're polar. Remember, nucleic acids are a organic macromolecule. We memorized that last time. So these hydrogen bonds will hold the two strands of DNA together. Hydrogen bonds are going to hold any large structures together, mostly proteins, though. Or as I said before, polypeptides or long chains of amino acids. What is a peptide? And you're going to learn that in a few. But a peptide isn't just another name for the covalent bond, nonpolar covalent bond between the hydrogen and carbon in amino acids. That's all that is. It's just amino acids bounded together. So whenever you hear peptide, think protein, think hydrophilic. Okay. Whew, crazy, right? So that electropositive hydrogen, I think we know this by now, because hydrogen's going to lose the electron more likely. Because the electron doesn't want to stay home. It wants to get the heck out, especially in the hydrogen. There's nobody else to play with, really, except for one proton. That's not a message. Okay, so electronegative is the oxygen. Okay, and you could have it between nitrogen atoms. So we're sticking to water here with hydrogen bonds. And the nitrogen atoms could imply large polypeptides. Yeah. So we'll talk about surface tension when we talk about water more. But surface tension, like, how could I explain that? I don't think any of us could walk on water, right? We can't walk on water. Right? Correct? We can't do that. I only heard of one guy ever doing that anyway. But a bug can walk on water, right? A bug can walk on water. So, and it won't sink. It goes through. So we have what's called surface tension. So those bonds between water, do you ever look at water when it's boiling? Sometimes it kind of swells up and kind of holds itself together until the boiling point goes over 212 degrees Fahrenheit. Then it kind of breaks up. But it takes a lot of energy. You know what I'm saying? Do you ever watch? I watch water boil all the time because I make oatmeal every day. So I'm in a rush and come on, boil. It never happens. So it takes a lot of heat. I got to crank that heat up just to change the liquid water into vapor, right? It takes a lot. 212 degrees, a lot of energy to put into that to change its shape. So that's important. And so water is going to hold on to a lot of heat. Like, did you ever notice when it's really, really hot outside, where's the best place to go? Not over here in the pond or in the East River, but where would we want to go to cool off a little bit, even without going in? Like, where is it cooler in the hot, really hot days? What would you say? More in the fields and plains or by the water?
Beach.
You go by the beach. I think the beach is a good place. I mean, not only because the wind is blowing there, but it is. But not only that, but the water is absorbing a lot of that heat. It kind of takes it out of the atmosphere. So you might be a little cooler, not every day, but in general. So the water is absorbing all that heat, and it kind of takes your temperature down a little bit of the atmosphere and your body temperature. I would imagine that would happen too. Don't look behind me. That's atrial fibrillation. That's not a good condition. That is an ugly condition, you'll learn. Okay. Let's move on. Hydrogen bonds, holding large molecules together, like proteins or nucleic acids, like DNA, right? How do I get rid of that? Oh, 3D structures, they call that. Yeah, I didn't mention that, three-dimensional, like a helix, like DNA. I can't draw helices, but there'll be a picture coming up. I told you this, yeah. So hydrogen bonds hold the strands of DNA and form between amino acids on a protein, but don't forget the word polypeptide. So polypeptide, like a protein, is 50 or greater than or equal to 50 amino acids, where polypeptide would be less than 50 amino acids. That's all that means. It's still the same thing. It's a long strand of amino acids, which you're going to learn are the building blocks for protein. It's building up, my friends. Okay, well, I showed you this. They do dotted lines as well. This is the hydrogen bonding, which forms between water molecules. You got to be careful with this. Hydrogen bonds are between water molecules. But what kind of bond is this between the hydrogen and the oxygen within the water molecule? Anybody remember?
Covalent.
It's sharing. That's a covalent. Excellent. And go a little further. What type of covalent? Is it polar covalent or non-polar covalent? It's polar. Water is freaking polar. That's the number one thing. If I ask you, right, say, you're walking down the street and you don't even know who I am because I'm on TV here, whatever this is, Zoom. But if you're walking out of the bodega and I say, excuse me, what's the most important quality of water? What are you going to say?
Polar.
You sure are. You sure are. And drink your Red Bull and go on your way. Okay, so acids and bases. We kind of know a little bit about that. And I think what I told you is basically all you need to know. But I want to show you what's going on with the pH thing. Okay, so some water molecules, all based on water and dispersing in water, they ionize. And sometimes you get more of these, and sometimes you get more of these. Proton. And I like this. I like what they say here. Like, remember hydrogen? What's the atomic number of hydrogen?
1.
How many electrons does hydrogen have in its stable form, in its Chon form?
1.
1. So if it loses an electron, basically all it's left is a proton. Does that make sense? Let's go back to the bodega. Oh, where are we? Chipotle, right? So, so now we go to Chipotle all the time. We're eating it all the time, which, and not necessarily you're going to get acid stomach all the time from eating Mexican food. That again is not 100% true. But let's say it's just happening to me. Every time I go to Chipotle, which I go every day, I get acid stomach to the point where and what are those tum-to-dum-tum? What are they made of? Like if I've been taking them at the bodega, I've been going to the bodega, I buy tum-to-dum-tum, and I eat the tums. What are tums made of? That
Calcium.
neutralize the acid.
Calcium.
They have calcium in them. That's true, but but that's not all why. It's bicarbonate. It's bicarbonate. Yeah, we're talking about acid base, but we're going to revisit that, Chris, the calcium part. So, and I'll probably go back to the same bodega. So the Tums aren't working. The bicarbonate's not working. So then now I have to go upstairs to the doctor above the bodega because I got to get something else. It's just not working. So do you know what they give you for that? Anybody know, like the little blue pill, which actually I think is all over the counter now, but stay with me.
Omeprazole?
What is it called? Yeah, you just gave me the chemical name, right? But it's like Nexium or something like that,
That's
right?
omeprazole.
Yeah. What do you know how they work?
Uh,
Do you know how exactly they work? I'll tell you. I'll tell you. In the stomach, right? The stomach. Everybody know the stomach? That's where your proteins are broken down, you know, to the end of your esophagus, which we're going to learn later. But your stomach has a lot of this stuff in it. Anybody ever hear this? HCl. That's hydrochloric acid. Ionic bond between hydrogen and chloride. I shouldn't write that the L big. I should write that small because I'm messing you guys up. Are you guys with me so far? Because now I got acid stomach from Chipotle, right? So now in the stomach, this HCl has to be broken down. You can't keep that in there. It's going to burn a hole in your stomach and give you an ulcer if it continues, if you don't have proper lining. But this is going to disperse to this and this. And acid stomach is too much of this. So tum-to-dum-tum didn't work. The bicarbonate didn't work with the bicarbonate acid. This didn't buffer it enough. So now I got to take something else, like Nexium, omeprazole, whatever it's called. So these are called proton pump inhibitors. PPIs. PPIs, that's what those drugs do. And what they do is they stop the mechanism that pumps out HCl in the stomach. It slows down the pump of HCl and the dispersion of ACL. So it decreases your hydrogen ions. Okay, so then I'd have to take a proton pump inhibitor. Everybody with me on this? But my point was I got excited because the book says that we call the hydrogen ion a proton. So basically, the proton is the hydrogen ion. That's my point. Everybody okay with that? Making sense? Okay, so acid is H plus and hydroxide is the not minus, it's an anion. That's more about alkaline, which is base. So a neutral, and this is in the laboratory, a neutral pH is said to be 7, and pH is percent of hydrogen. But look at the number, the way it really is. It's -7, but we, for some reason, we just shortened it and divided it and just say 7. But in theory, it's 10 to the -7th. Are you guys with me here? 100 million, whatever it is, molecules of, not molecules, ions of hydrogen to the -7 point, whatever, you know. So this is a minus number, an inverse scale, but it's still 7 on our scale, the pH scale. So that's really why those numbers, some books have a nice like table of it showing you the range, but it's kind of simple to remember. And that's all you have to do is remember that 7 is neutral in the laboratory, and anything above 7 is alkaline, lower concentration of hydrogen. So that's another thing, maybe say concentration of hydrogen. pH is just a scale. So the higher the pH goes, the lower the concentration of hydrogen. And usually concentration is drawn like this. That means concentration. So the increase in hydrogen concentration, that would be decreased pH. So it's inverse scale. So less than 7. And in the blood, less than 7.4. Rock and roll. Okay, so when a solution has more hydrogen ions, it's called an acid. pH falls below. A proton donor, of course. When the solution is more hydroxide, it's going to be called base. Or is the word alkaline on here somewhere? Here you go. Yes, question?
Yeah, I got a question. How many moles of hydrogen does it take to go down in the scale?
It's a lot. That's a good question. It's like times 16. So here's a good question. So like if something's like, say a pH of something is 6.5, right? And things we eat are 6.5 pH, like maybe a tomato, right? A tomato, something like that could have enough acid to lower the pH to 6.5. But if you go from 6.5 to 6, that's a huge jump. That's a huge jump in acid if that's going to affect your blood, you know? So in a laboratory, that means a lot, but it also means a lot in your body. That's why we have so much bicarbonate in our body, in our blood cells, in our blood, to keep buffering all those free hydrogen ions, because it's happening all the time. Do you know every time a molecule of hemoglobin binds a molecule of oxygen, it gives off a hydrogen ion. So there has to be bicarbonates right in our red blood cell, or else we'd have acidic blood and it would be destroyed. And acidosis, which is, you know, acid in your blood, is a very hostile environment. It'll destroy the proteins. And you're going to hear a word called denaturing a protein, right? Denaturing a protein. That means it's breaking up the shape. Like, here's a good example. And I did this morning, right? You go over to the, now I'm heating up a pan, right? Then I get the eggs out and I crack the eggs. I get rid of the yolks. Sometimes I give them to the dog. I don't know if that's good. And then I put the egg whites, which, why do they call them egg whites when they're clear, right? They're clear inside the egg. I put them in a bowl too, so I get a nice, make sure it all cooks at the same time. So I can see I can see right to the bottom, because I can see all the shells that I screwed up and put in there. So it's clear, and it's protein. It's a protein called albumin, which is a protein. So it's going to be more than 50 amino acids bound together through peptide links. So now it's clear, but then I add it to, I don't know, 200 degrees or sometimes 300 degrees. That's a hostile environment. So it's going to totally denature that shape of that protein that's held together by hydrogen bonds. So the shape of that protein is going to be destroyed because I added so much heat. What's my point about this? The shape, right? The hydrogen bonds, the shape of it. So my point is this. Now it came back to me. So acid blood is a hostile environment that has to be maintained through these homeostatic feedback mechanisms, just like body temperature. Because, you know, when you have a fever, especially in a newborn or something, a baby, right? That fever can go up to buck 200, 204. That's a hostile environment. You're going to start to destroy your own protein. And what did I tell you about protein? It's your structure, right? So it denatures. But acids really denature proteins quick, and it really stops it makes you sick. Let's just say that for now. Your physiology, it makes you sick, your physiology in your body.
So the acidosis in the blood is kind of like the hot pan to the egg.
In a way, yeah. Yeah. I mean, there's no place in our body that's acidic except for the stomach. Nowhere else. Maybe the vagina at certain times of the month can be acidic during certain times, but nothing compared to the stomach. Could be almost zero, but nowhere else. And think about this for later. Like when you're in the stomach, there's enzymes in there. Enzymes are proteins. So think about the evolution of the pepsin, which is a protein enzyme that breaks down protein. It breaks down protein. It's like a cannibal, but it's only in the stomach. So how does it survive under those conditions? And it's just evolution. It's just, that's the way it goes. How anatomy mirrors physiology. Mother Nature's a mad scientist, my friends. Okay, so pH scale. So the pH scale, I think we all agree, runs from 0 to 14, 7 being in the middle. 0 is the strongest, 14 is strongest acid, and 14 is the strongest base. So then we have to divide it into 1. That's why we get negative numbers. Well, I'm not going to ask you to do this. Okay, so it's an inverse logarithm. So technically, a pH of 7 is 10 to the minus 7, right? So you got to move that decimal point, 8 times, whatever, and get a number something like this. Hydrogen, that's the concentration of hydrogen per milliliter of water. So that's why it's inverse. I hope that makes sense. I guess this helps. This helps. This pH scale helps because it kind of gives you the concentration is a positive number here, and again, a negative number of OH in acid. So it's completely opposite. Like as the hydrogen concentration is going up, the hydroxide concentration goes down. And these are negative numbers. I don't know if you can see that negative. These are negative. So it's an inverse logarithm, and we're just going to live right here, my friends, in physiology, in this BIOL class that we're all sitting in for hours. Okay, so we need a buffer. We just need a buffer to buffer, and it's mostly about buffering acid, but sometimes you have to buffer the alkaline too. So the buffer could be either a weak acid or a weak base. And here's our favorite buffer, and that's the bicarbonate ion. Tum-ta-dum-tum. So if mixed with those hydrogens, it becomes this, and this is carbonic acid. This is carbonic acid. So if you mix the two, this is really high in your blood. Really high in your blood. Well, it should be homeostatic in your blood. I'll give you those numbers when we get there. Probably when we do digestion or respiratory or kidney, one or the other, because it has to do with all of them. But mostly kidney. I was talking to you before about the guy with emphysema. So he has a lot of CO2 in his blood, which means he's got a lot of free hydrogen. So the compensatory range, because it's the lungs that are failing. So the kidney is going to get involved and try to compensate for that lowering of the pH. And it's going to start to hold on to more bicarbonate ion. Your kidney, it does a lot of filtering and reabsorbing. So it's going to hold on to more of this to buffer more hydrogen, and you'll have more of this in your blood. So this is carbonic acid. This is the bicarbonate ion. So the bicarbonate ion really is what does most of the acid buffering. And then the carbonic acid, and there's another side to this equation, which should be coming up soon. Okay. That has to do with carbon dioxide. Oh, here's your compensatory ranges, right? But I'm going to tell you, I don't like this. I'm not comfortable with this. I mean, because this is the compensatory range. Between what two organs? Pretty much always the kidneys and lungs. So the urinary system and the respiratory system. But if my pH of my blood is 7.39, I don't care. That is acidosis. I just got to find out why. Am I holding on to too much CO2? And that would be a problem with my lungs. Am I losing bicarbonate from where? Sorry, HCO3 minus. Or low bicarb, that would be a problem with my kidneys. And these two got to fight it out to keep my pH in that range. Hope you understand that, because that's a big physiology topic right there. Okay. Oh, in organic molecules. Let's take a break. Let's go down the street and get some Red Bull. Whatever you guys need to do. What time is it in the real world? 3:45 around? 3:45. We're here till 5:21. Okay. You guys don't mind staying until 8 o'clock, right? So we can go into cell? No problem. No problem. Yeah, let's stay. Let's stay. Okay, so it's 3:45. Let's come back at 5 after 4. Deal? So let me write that in the chat. I like to write that in the chat. Be back at 4:05 p.m., which is Zoom cameras on, right?
I had a clinical question.
Shoot, wait a minute. I just said that to one person. Hold on a second. Let me get that. I thought I knew what I was doing. There we go. I'm sorry, Claire. Go ahead.
No, I was just curious as we were kind of connecting water as like a mechanism of absorption of heat, and when we were discussing like fever. And I was just curious as to, because oftentimes it's like, keep your fluids up if you're running a fever. So clinically speaking, does that have a big impact on like breaking the fever, especially in like infants and children that can reach such high
Good
temperature?
question. It's a good question. Yeah, that should help, but it's not. You really got to lower the body temperature.
Right.
Usually when you have a fever, you tend to suck more of your fluid and oxygen too. You tend to get more oxygen into your cells. You tend to take more water into your cells. So it's taking it out of the blood. So did I mention fluid compartments last time? I have a vague remembrance of that. Okay, because that's a big part of physiology. So osmotic pressure, we got to talk about osmosis. So when we do the cell, so water will tend to come out of the blood. Oxygen will come out of the blood when we have a fever, and that will kind of empty your blood of fluid, and that's true dehydration. So when you have a fever, you worry about dehydration more than any of the other things. The fluid's going into your cells, but your blood levels are going low. And this is really important, actually. It's a really important question for the physiology and clinical view. So if my blood levels of water goes low, but due to dehydration, like if I have a fever, so a child is all water, a baby, I should say, is all water, and their body volume is so small. So this is a massive effect, having a fever and being dehydrated, two really bad things you don't want to happen to a newborn, because things could escalate very quickly. So you tend to get dehydrated, and that's really why you're giving more fluids. Because if you're dehydrated, your blood volume goes down, right? Your blood volume goes down. And what happens to your blood pressure when your blood volume goes down? No, it goes down. Yeah, it goes down. And for the most part, again, we're so worried about high blood pressure, but our bodies are more in tune to raising blood pressure because we're so worried about losing blood. So it's going to drop your blood pressure. That may affect your cardiac output and your blood delivery, which is oxygen delivery to your brain. So water is going to help maintain all of those things. It's going to keep your blood volume high. But I think your question was about temperature.
Yeah,
I think your question was about temperature.
Yeah,
But I can't answer that directly because I don't know.
No, I know it makes
It
sense.
might help. It'll help.
It was helpful because
Yeah.
I think just in general, clinically speaking, it is more complex than just
It's
that.
much more complex. Yeah. It's like you're not drinking that water to cool your body down. You're doing it to keep your blood volume high and not to get dehydrated, which is really a problem with cardiac output. And it's going to increase your heart rate because your heart rate has to respond. This is a good physiology question.
Yeah.
But temperature is that's a hard question to answer about temperature. I don't know.
Right. That was like my biggest
based on
thought.
water in there.
Yeah.
Doesn't like a regular blood volume kind of help the body do what it needs to do?
It does. That's right. That's
So, like, the
exactly right.
temperature and everything.
Yeah,
like,
it keeps it homeostatic. Yeah. But temperature, it depends on everything else too. Like, again, your body temperature is going up. So, again, that may lower it a little bit, but I don't think it's going to make a big effect right away. You better put that person or that child in a hypothermic bath or a therapeutic hypothermia.
Like,
That's a really good question.
Does it have the same heat absorptive factor as in like submersion in water?
No, not exactly. No. Good question. So, but it does help. I mean, it'll help slowly maybe lower the temperature of a fever. But what's causing the fever too is a whole nother thing.
Yeah,
I can go on and on. I can go on and on.
Yeah.
About what's sending the message to the hypothalamus to raise the body temperature. That's another thing. Plus, who knows? Maybe what if the baby has diarrhea? She's becoming dehydrated from that, or something worse like constipation or spastic colon. I mean, I can go on and on about it.
Yeah, it's super complex.
So yeah, it's a complex question and not that simple of an answer, but good one. All right, so I'll see you guys back at 8 o'clock tonight. 4 o'clock, 4:05. I'll see you then.
Professor, did you take attendance?